Shri Gurubhyom Namaha. This is class 9 physics and we are dealing with the chapter Force and Newton's laws of motion. So we'll just have a recap of the previous sessions, what and all we have learned. We have seen about the force, the types of force, and we have seen about the Newton's first law of motion, which is also called as law of inertia. What is inertia, the types of inertia, and Newton's second law of motion. In today's session, we will derive the mathematical formulation of Newton's second law of motion, that is F is equal to ma. Before getting into the derivation, we'll just see what is the Newton's second law of motion. So the Newton's second law of motion states that the rate of change of momentum is proportional to the force applied to make the change and takes place in a straight line. So already in the previous session we have learned about momentum. So if any object is going to have a mass and it's going to be moving, then the quantity which describes it, the object which is in motion, we call it as momentum, right? So this is what we have seen, and we are going to derive the very famous relation F is equal to. So just a small recall, what's the formula for momentum? So momentum, we know that is P is equal to M into V. Momentum is denoted by the symbol, by the letter P, and it is equal to the product of mass and velocity of the object. So M is the mass of the object, V is the velocity of the object, and there's a unit of momentum is kilogram meter per second. So now we will derive the mathematical formulation of the Newton's second law of motion. So what we are going to do is we are going to consider an object which is having a mass m. And now this second we are talking about motion only. So the objects are going to move. So the initial velocity of the object is going to be u, and the object is uniformly accelerated. So there is a change in velocity of the object. Object becomes v, and this takes place in a time of t because the object is in motion. So any object which is going to move, it will be first it will be at one position, and after a certain time it will be in another position. So it takes a particular time. So we are representing the time as small t. So we also know that momentum is nothing but mass into velocity. So we are going to find what is the initial momentum. So your initial momentum P1 will be nothing but mass into initial velocity of the object. So we can also write this as P1 is equal to m into u. Similar way, what we are going to do is we are going to write for the final momentum here. So your final momentum will be nothing but your P2 is equal to mass into final velocity. So P2 will be equal to m into v. Now we are going to find what is the change in momentum. So change in momentum is nothing but we need to find what is the difference in the momentum, that is your final momentum minus initial momentum. So you can write this as change in momentum is equal to P2 minus P1. So now we'll just substitute the values of P2 and P1. So P2 is our final momentum and P1 is our initial momentum. So when you substitute these values, we will get mv minus mu. So what is common in that equation? That is the mass is common. So when you take m out, you will get m into v minus u. That is mass into final velocity minus initial velocity. This is the change in momentum of the object. Now we are going to find what is the rate of change in momentum. Okay, Always remember, whenever we come across the word rate of, it represents that the uh, quantity or the motion is being taking place at a particular time, or any physical change or chemical change, whatever it is. When we come across the time, that particular thing is happening at a particular rate of time. So that's the reason we say that rate of time. So we will be dividing the equation by t. So we are going to find at what moment, at what time the change in momentum has been taken place. So your equation will become as m into v minus u by t. So the change in momentum to take place in a particular time because the object is in motion. So according to the law, what is the law stating? So the Newton's second law states that the rate of change in momentum is going to be directly proportional to the force, and it is going to take place in the direction of the force here. So we are going to relate this equation with respect to the rate of change in momentum. So your force will be directly proportional to rate of change in momentum. So the rate of change in momentum, what we have found, it is nothing but F, that is this is your proportionality symbol. So here we have this is our proportionality symbol, this is our proportionality symbol, and we say that the force is directly proportional to the rate of change in momentum. So F is directly proportional to m into v minus u by t. So this proportionality symbol we can remove, and we are going to give it as a constant. Okay, so always, even in maths or in any other physical quantities, or when you derive a relation, the proportionality symbol we can remove it and we can give it as a constant. So this constant of proportionality will tell us how much the value are going to increase or decrease here. So here this constant of proportionality, we are denoting it as small k here. So small k, in many places we can give as x or y or z. It depends upon whatever term letter we want, we can use it. Okay. So, and we also know that what is acceleration? Acceleration is nothing but rate of change of velocity with respect to time taken. So now if you see this equation, we have got F is equal to K into M into V minus U by T. So this is nothing but our acceleration here. Okay. So now we are going to substitute this value in the above equation. So when you substitute that, we will get F is equal to K into MA. Okay. So because we know already our acceleration is nothing but rate of change of velocity with respect to time taken, which we have learned in the first chapter. K is nothing but constant of proportionality. And for getting 1 unit of force, what we are going to do is we are going to find something here now. It is SI unit of mass, we know it is 1 kilogram, and SI unit of acceleration is meter per second square. So for 1 unit of force, what we are going to do is we are going to choose the constant to be 1. Only when we choose the constant K as 1, we will get the force as 1 unit or 1. Otherwise, you will not get the original value of the force. So this constant K will be depending upon different situations, or different, it will be depending upon what physical relation we are deriving, all those things. So here for 1 unit of force, I have told that K is equal to 1, and I'm also going to consider that the mass is also going to be 1 kilogram, and the acceleration is also going to be 1 meter per second square. So 1 unit of force will be equal to, that is K's value is going to be 1. So 1 into 1 into 1, it's going to give us 1 unit of force here. So we know in the previous slide we have seen, we have got F is equal to MA. Now instead of this K, I am going to substitute 1. So when you're going to substitute 1 here, what we will get? We will get F is equal to ma. So this is our mathematical relation for Newton's second law of motion. Okay, F is equal to ma. The SI unit of force is Newton, or you can also write this as kilogram meter per second square. We can also define the unit of force. One unit of force is defined as the amount that produces an acceleration of 1 meter per second square in an object of 1 kilogram of mass. So in this session we have seen about we have seen the derivation of Newton's second law of motion, and in the upcoming session we will solve few numericals and we will move on to the Newton's third law of motion. Thank you, children.